This video is to help prepare you for both the average rate of change and the instantaneous rate of change. Now this is actually the second part of two videos, where the first video just talked about preparing for the average rate of change. Now looking at an example that we used in the previous video, if we have the function f of x equals to x squared, which is the graph of it is the one in black, the parabola or U-shaped one. And what we had found in the previous video was what was the average rate of change of the function from x equals to -2 to x equals to 3. And the line that helped us find that average rate of change is the one in red. But then what if we chose an even closer value to 3? What if we said from 0 to 3? That would be the one in the line in blue. Or what if we said from even closer, from x equals to 2 to x equals to 3? That would be the line in green. And what if we got even closer to that? What if, let's say, from x equal to 2.9 to x equals to 3, or x equal to 2.999999 to x equals to 3? So what happens if we get infinitely close to 3? Then what we would end up calculating when we found the rate of change of that line as we get closer and closer would be the instantaneous rate of change. Now this is actually a calculus topic, but to be able to even do it in calculus, we first need to know some algebra techniques. So let's review a couple special types of functions that we had, or expressions of functions, when we first were talking about an introduction to functions. Now the first one is, what if we had to calculate g of x minus g of a all over x minus a, when, let's say, we had the function g of x is, let's say, 1 over x minus 1. So if we had to find the simplified version of this expression, g of x minus g of a over x minus a. So one thing to remind you, first, g of a, that would be simply replacing, wherever we see x, we will replace it with a. So that would be 1 over a minus 1. So g of x minus g of a, just looking at the numerator of that expression for now, that would be, well, g of x, that was 1 over x minus 1, minus g of a, that was 1 over a minus 1. And then remember to combine two fractions, they need to have a common denominator, which in this case, the common denominator, the LCD, the least common denominator, would be a minus 1 times x minus 1, or x minus 1 times a minus 1, whichever one you want to write it as. So for the first fraction, we'd have to multiply top and bottom by a minus 1. So we get 1 times a minus 1, which would just be a minus 1. And on the bottom, we'd have a minus 1 times x minus 1. And then for the second fraction, to write it with this common denominator, we'd have to multiply top and bottom by x minus 1. So again, 1 times x minus 1 would be x minus 1. And then we'd have a minus 1 times x minus 1. So now that they have a common denominator, you just subtract their numerators. But remember, this minus sign is for all of that numerator. So writing it as one fraction with that common denominator, we'd have that a minus 1, and then minus all of the numerator of the second fraction, so x minus 1 inside that parentheses. So let's see, distributing that, we'd have what? A minus 1 minus x plus 1. So those 1s and the minus 1 would actually cancel. So that would be a minus x over a minus 1 times x minus 1. And then, remember, that's not what we were trying to find. We weren't trying to find g of x minus g of a. We're trying to find g of x minus g of a divided by x minus a. So that would be, take what we just got, oops, divided by x minus a. So we take that a minus x over a minus 1 times x minus 1, divide that all by x minus a. Now remember, dividing by x minus a, that would be the same thing as multiplying by 1 over x minus a. Just like dividing by 2 is the same thing as multiplying by 1/2, or dividing by 3, same thing as multiplying by 1/3. So dividing by x minus a is the same thing as multiplying by 1 over x minus a. Now, one reason why we do this, well, let's see. In the numerator of the first fraction, we have a minus x. In the denominator of the second fraction, we have x minus a. Now, one thing, we could rewrite the numerator of the first fraction, factoring out a minus sign, so that would be minus, we could write it as minus x, the quantity x minus a, because if we distribute that, you'd have minus x plus a, which would be a minus x. And let's see, so we'd have, again, over that a minus 1 times x minus 1. And now the reason why I did that is now that x minus a, those factors cancel that we had both in the numerator and denominator. So in the numerator now we just have a negative times 1, so it'll be negative 1 all over that a minus 1 times x minus 1. Now, as you'll see when you take calculus, that you'll be able to use this expression further to see what happens as, let's say, that a gets really, really close to x, to any specific x value. Now, another example of an expression that is useful for when we're finding that instantaneous rate of change is what is known as the difference quotient, which is f of x plus h minus f of x all over h. Now this is very similar to the one above, and it's actually in some ways either one can be used. There's just in this case what they talk about is what happens when h, which is the difference between the top and the bottom, gets really, really close to 0. So let's say if we did this for the function f of x equals to x squared minus 2x. And we had to find what is this expression, f of x plus h minus f of x all over h. So the first thing I would do is to figure out, okay, what is f of x plus h? So remember, that means wherever we see x, we plug in x plus h. So we would have, instead of x squared, that would be x plus h squared, minus, instead of 2x, it'll be 2 times the quantity x plus h. Now, one thing to remember, because this is a common mistake for many students, you cannot distribute that square inside the parentheses when you have a plus or minus separating terms inside the parentheses. So, but remember that x plus h squared, that's the same thing as x plus h times x plus h. And let's see, I could also distribute this negative 2, so this will be minus 2x minus 2h. Now, falling out, when you multiply those two binomials, the x plus h times x plus h, we'd have x squared, then multiply the x times h, so hx plus another hx, so we'd have plus 2hx. And then multiplying the last terms, h times h, we'd have plus h squared minus that 2x minus 2h. So that's just what f of x plus h is. And then taking that, well, the numerator was not just f of x plus h, it was f of x plus h minus f of x. So we take what we just found in the previous step, all of that x squared plus 2hx plus h squared minus 2x minus 2h, subtract off f of x, which was the original function, this x squared minus 2x. Now, one thing, when we distribute that minus sign, you'd have an x squared minus x squared, so those actually cancel. And then you'd have a, oops, that was a minus 2x. About to say something's not right there. And then we have this minus 2x, and there's this minus a minus 2x, so those cancel. So we'd have left over 2hx plus h squared minus 2h. And then, remember, really what we were trying to find was this f of x plus h minus f of x, taking all of that, dividing by h. So this would be, well, we found the numerator was 2hx plus h squared minus 2h, dividing that all by h. And now there's a couple ways you could think about this. One way is that if you notice in the numerator, each one of those terms has a factor of h. So I could factor out that h. So you'd have h times the quantity 2x plus h minus 2 all over h. And then we could cancel those h's. So we'd have left for that difference quotient would be 2x plus h minus 2, which would be the answer. Now you also could have thought of it, just some students like to think about it this way, that dividing that all of that numerator by h is dividing each one of those terms by h. So we'd have 2hx over h plus h squared over h minus 2h over h. And looking at each one of those terms individually, let's see, here the h's cancel, so you'd have that 2x. Here one of the h's cancel, so you'd have plus h. And here those h's cancel, so you'd have minus 2. So either way you do it, you notice you do get the same answer. Now, this is to help prepare you for when you're finding the instantaneous rate of change. It also helps remind you of evaluating functions when they're not just constants.